Hello students, very good afternoon. My name is Ravi Ranjan Kumar and I welcome you all to this session. This week we are going to cover properties of matter. Okay, in the first two lectures we will be covering viscosity, and the next two lectures will be about surface tension, and the last lectures will be about elasticity. So here let's start with viscosity. And let me share my screen with you guys. So here we go. So let's start with viscosity. As we all know that viscosity is a property of fluid by the virtue of which adjacent layer of fluid, if they have a tendency of relative motion between them, they opposes the tendency of relative motion between them. Okay, and that phenomena is known as viscosity. Okay, and we are going to look into the quantitative aspect of that phenomenon. Okay, so let's start our discussion. Viscosity. So let's imagine there is some liquid flowing over a surface. Okay, and let's define our coordinates also. Let's say this is origin and this here is y-axis. And let's imagine a thin layer of liquid like this. Okay, and say this is y and thickness of this thin layer is d. Okay, so let's say this layer here is moving with some velocity v. Okay, and the layer which is at y plus dy is moving with velocity v plus dv over here. So here the way we have shown that we are seeing that when y is increasing, okay, velocity is increasing as well for the layer. So now you can see that when we consider the element, this element of liquid, the fluid above it is moving with larger velocity, and fluid below it is moving with a smaller velocity. Okay, so what will happen? So the lower layer will try to oppose its motion. Okay, and it will experience a force F, let's say, in backward direction, and the upper layer here will try to drag it, okay, in forward direction. So it will be applying some force, let's say F plus dF over here. And the expression of this force is given by, the expression of this force here will be given by F is equal to minus eta times A into dV by dy over here. That is a simplified expression for viscous force. This expression is for viscous force here. And we are going to look into each and every term, okay, of this expression. So first of all, F here is viscous force. A here is the surface area of layer of fluid. Okay, and obviously this F here, as you can see in the diagram, is acting along the surface area. Okay, that means tangential to that area. Okay, and eta here we have represented, that would be property of the fluid, and that is nothing but known as viscosity of fluid. And this term dV by dy is rate of change of v with respect to y, and this term is known as velocity gradient. Okay, so this is the expression. We will be dealing with this equation a lot in different problems. But before moving ahead, let's talk about this property of liquid, which is viscosity of fluid. Okay, so let's talk about viscosity of fluid. Okay, so as the expression, the above expression suggests, okay, the dimension of this physical quantity, which is viscosity of fluid, will turn out to be ml minus 1 t minus 1. So here, basically, the SI unit we will be able to say SI unit will be Newton second per meter square over here. But the more realistic unit that we will be using more often, that would be its CGS unit, and you must understand about that as well. So CGS unit, you must understand the unit of force is Newton in SI unit. So in CGS unit, it is dyne. Okay, dyne second, and the unit of length is centimeter. So dyne second per centimeter square, and this term here is known as poise. This term here is known as poise after the name of famous scientist Poisley. Okay, and when you will convert this CGS unit and this SI unit into each other, you must realize that one poise is nothing but 0.1. Okay, uh, Newton second per meter square, or alternatively you can say 1 Newton second per meter square is nothing but 1 decapoise. Okay, so basically 10 poise you can say. Okay, so this is the conversion of unit. So generally, okay, the unit given in the question is poise, so you must clearly understand that poise is nothing but CGS unit of viscosity. Apart from that, viscosity of fluid is property of liquid which vary with respect to the temperature of the liquid also. Okay, so let's look at this aspects, and that is for your information. First information is that viscosity of liquid decreases with increase in temperature, and the proportionality, eta would be, or eta liquid you can say, would be inversely proportional to root T, where T would be absolute temperature. That is an approximate relationship. And gases behave differently. So you can say viscosity of gases you can say increases with increase in temperature. And the relationship over here, eta gas is directly proportional to root T. So these two things are for your information. And apart from that, what I urge you to please understand that what one poise is. And if you need to convert one poise into SI units, that you can do as well over here. So now look into the other aspect of the problem. Okay, the first problem here I am going to discuss about is something called linear velocity profile. Linear velocity profile. And linear velocity profile can be approximated uh, when layer of liquid is thin. What I mean to say here is, let's say there is a fixed surface, and over that a thin layer of liquid is flowing. Okay, and let's say this thin layer height is say h. Okay, and let's say here we have some plate, or let's say this is enclosed between two plates. Okay, and this area, the area of this plate is A. Okay, or dimension of it is L cross L. This is say a square plate, and when I say that the layer of liquid is thin, what I mean to say that H is much less than L. So when H is much less than L, we can assume the linear velocity profile. For example, if the upper plate is dragged externally with some constant velocity V0 by applying some external force. Okay, so the since this h is very small, the velocity profile that would be created would be like this. The lower layer of the liquid, since it is in contact with the stationary plate, will not be moving at all, whereas the upper layer of the liquid okay, which is in contact with the upper plate, will be moving with the same velocity as V naught. So the velocity profile that would be created is this layer of liquid will be moving with V naught, and this layer of liquid will be moving with zero velocity. So a linear velocity profile will be created, because if this h is very small, if there is like curved profile also, you can approximate it with linear profile here. Okay, so here in this case, it is very easy to find out the velocity gradient. So dv by dy here will be nothing but equal to simply v naught by h. So in other words, you can simply write v is equal to v naught by h into y. That means to say, like for example, if we choose a thin layer of liquid here, okay, so this layer of liquid, you can say, would be moving with v velocity, and this layer of liquid, you can say, moving with v plus dv velocity, and v is this. Okay, and now you must realize, since there is relative motion between the adjacent layers over here, so what you can say, it will be experiencing the viscous force over here. So the bottom part of the liquid will exert a force. In backward direction, this force is F, and this force exerted by this layer would be F plus dF over here. Okay, so now you see, in this question, we need to find out several things. Like for example, first of all, what would be the force? What would be the value of this force if we are exerting some external force over here? Okay, what would be the magnitude of this external force in order to move the upper plate with constant velocity? So now you must realize, first of all, we must find out the magnitude of this viscous force. So as we understand, like F is equal to the magnitude only we are writing, F will be equal to eta times A times dV by dy, and dV by dy we have already found out. So eta and A would be nothing but L square, and dV by dy is nothing but V naught by X. So this is the force. Okay, and a few things I want you to realize, that for example, if any layer of the liquid is moving with constant velocity, means velocity is not changing with respect to time, that means that the net force acting on this will be equal to zero. So basically in this linear profile also, you can see that the df is turning out to be 0, or df by dy, if you want to say, that is turning out to be equal to 0. That simply means that the net force acting on any layer is going to be equal to 0. So now in order to find out the F external, what we can do, just closely look at this. Let's imagine a layer of liquid which is in contact with this plate over here. So obviously the plate will be exerting the viscous force, or plate will be exerting some contact force, and the lower layer of liquid will be exerting viscous force on that. So obviously, if this layer of liquid is moving with constant velocity, the force it exerted by this plate on this bottom layer will be same as F. So this layer of liquid will again exert equal and opposite force on the plate, and that is going to be equal to F. And now you can see, since the plate is also moving with external with velocity v naught, and that is uniform, so that means net force acting on the plate also should be equal to 0. Now you see, F external is applied by external agent, whereas this force F is applied by the liquid in contact. Okay, so obviously F external is going to be equal to F, and whose magnitude we have already found out, and that is eta L square into V naught by H. So that is the magnitude of external force which we need to apply on the upper plate in order to move it with constant velocity. Okay. And another thing, let's try to find out like what would be the volumetric flow rate of liquid, okay, between these two plates. Next thing we want to find out is volumetric flow rate. And now you should realize that each layer of the liquid is moving with different velocity. So what we can do, let me draw the diagram here again. Okay, so this layer here is moving with say velocity is equal to which we have already found out, that is V naught by H times Y. Okay, and see, so what would be the volumetric flow rate dq through this cross section? So this dq will be equal to the cross sectional area of this part dA into this V. So what would be the cross sectional area of this? The dimension of this plate is L into LUC. Okay, so that means the cross-sectional area which we are thinking about is like three-dimensionally you can imagine. So this is basically dy, and this would be three-dimensionally you imagine this is dy and this is L. So obviously the area here would be nothing but L dy, and whereas V we have already found out, that is V naught by H times Y. So when we will be integrating this term from, let's say, 0 to capital H, okay, what we will be getting here is simply V naught L into H by 2 over it. So that would be the volumetric flow rate of the liquid between the two plates over here. And let's try to look at other aspect of this. Now, the third or the next thing we want to find out here is rate of work done by external agent. Okay, so external agent, let's say this is the upper plate, and this is moving with velocity v naught. Okay, and we are applying force externally on it, that is F external. Okay, so what would be the power delivered or rate of work done by external agent? P external, you can see, is going to be simple F external dot V. Okay, and F external magnitude we have already found out. The magnitude here we found out was nothing but eta L square into V naught by H over here, and V naught is a constant. So when you will be substituting these values, eta L square V naught by H into V naught over here, what you simply will be getting eta L square V naught square by H. And you must realize whatever is the rate of work done by external agent, okay, that work is not gonna stored with or not gonna be stored in some terms of potential energy. Rather, it would be dissipated in form of heat. Okay, so you must realize this P external is basically negative of P dissipated, or negative of this amount will be dissipated. Okay, so simply the rate of heat dissipated would be negative of this quantity, that would be minus eta L square V naught square divided by H over here. So this is another aspect. And one another thing I want to understand you here is say this was the upper plate and this was the lower plate. Okay, and let's imagine, okay, this layer of liquid to be divided in two parts. So what we are required to find out, what is the rate of mechanical energy transferred by the upper half of the liquid to lower half of the liquid. Now you see, upper half of the liquid is exerting, it will be dragging the lower half with this force over here, and this force, the magnitude of this force, we have already calculated. So that is eta L square, or eta, and that force was eta L square into V naught by H over here. And now you see, like this layer of the liquid is moving with what velocity? The velocity expression was V is equal to nothing but V naught into Y by H, and here at Y is equal to basically H by 2. You understand, that is Y is equal to H by 2. So this term will get converted into V naught by 2. So here, if we want to find out the rate of mechanical, or simply dW by dt over here, so that is again gonna be F dot V, and the angle between them, as you can see, is 0 degrees. So this will be simply F times V. So F obviously is eta L square V naught by H, and V is nothing but V naught by 2. So what we are getting over here is eta L square V naught square by 2H. And that is a very, very important problem you must see. So in this problem, okay, the first thing I tried to say was like when you can assume a linear velocity profile. Linear velocity profile simply means that velocity gradient would be a constant term, or you can say velocity will be varying linearly with y. Okay, so if you can do that, you can do that only when the layer of the liquid is thin. And when the layer of the liquid is thin, we try to find out, like we realized that the force experience or viscous force would be a constant, because we said that any layer of the liquid, since it is moving with uniform velocity with respect to time, okay, the net force acting on it got to be equal to 0. So like in the diagram I show you, like for example, uh, in this diagram only, like it is experiencing F due to the bottom part of the liquid. It is experiencing F plus dF in the opposite direction due to the upper part of the liquid, since net force on it got to be equal to 0. So dF is equal to 0. Okay, so that is what we expect, and that gives rise to linear velocity profile. And here, as you can see, we have got force as constant, means that is not varying with respect to y. F is independent of y. So from there we see that if we want to move some plate over a liquid surface, okay, we need to exert some external force, okay, and that will cause the uh, plate to move with constant velocity, you see. And see, so that external work will be doing some work, that external force will be doing some work over here also. So that means that energy will be transferred to the system, and that energy will simply be dissipated as heat. So each layer of liquid is doing some work which is transferring it to the another part layer of liquid, and that we have found it in the last part. Okay, so next thing, let's discuss next problem of the linear velocity profile only. Let me describe the problem to you. Okay, let's say here on this table we have a thin layer of liquid, say of height h. Okay, let's say this is some oil, okay, of viscosity eta. Okay, and over that there is a block of mass m which is connected with a pulley here, okay, with the help of an inextensible massless string, and here a block of small mass small m is suspended like this, and this thing has been released from this, that t is equal to 0, v is equal to 0, and we wish to find out, like when once this is released, okay, so obviously this will pull this block Okay, in rightward direction, what we wish to find out is the velocity of block of mass m, okay, as a function of time. Okay, so now you must realize, apart from the gravity that is acting on the system, okay, on this block here, a viscous force, you must not say viscous force, but the force uh, generated due to the viscosity over here, as we discussed in the last problem, that we can choose a thin layer over here. Okay, so this thin layer is experiencing a force in backward direction. So the upper, since it is moving with constant velocity, this block will be exerting a equal magnitude force in forward direction. And since this block is exerting force on liquid, liquid will be exerting force on the block in opposite direction. So basically, the magnitude of this force which the liquid will be exerting on the block will be same as viscous force. So let's say this force, the magnitude of this force over here, F will be simply, let's say, this is the area, this area that is in contact with it is A. So F is equal to, you can simply say, its magnitude would be eta times A. And since this layer is thin, we can assume the linear velocity profile. That means the velocity gradient will be constant. And let's say at any instant, this block is moving with velocity V. Okay, so this V by h would be the velocity gradient. Please understand that this v is variable. So this is the force exerted by the liquid on this block. So when we will be writing the equation of motion throughout, so that simply will give us the net pulling force would be mg minus this f, that is eta times a divided by h into v, and that will be equal to nothing but mass times acceleration of the system. Okay, so that net mass of the system is nothing but capital M plus small m, and that multiplied with dv by dt. So that would be the equation of force over here. Okay, now you see, so what we have got here is a differential equation in V and T, and when we will be rearranging this we will be getting as dV is dV divided by mg minus theta A by h into V, and the another side we will be getting as dt divided by capital M plus m. Now we can integrate both sides to get the velocity as function of time. Initial values are given that at t is equal to 0, v is equal to 0, and at t is equal to t, we wish to find out the value of v. Okay, so when you will be solving that, okay, so you know the solution to that, like v will be of form some v naught into 1 minus e to the power minus kt, something like this, where you must realize v naught is nothing but this quantity divided by this quantity, so that would be mgh divided by eta a, whereas k would be nothing but this quantity divided by this quantity over here, so eta a by m plus m times h. Okay, so you can see that the velocity of this block here is varying exponentially, and you must realize this v naught, this value of v naught is nothing but terminal velocity also, because you can see that for example at t tending to infinity, means after a very long time, okay, the value of v is going to be equal to v naught. At t tending to infinity, you must also realize that the net force on the block got to be equal to 0. So you can also say that mg is equal to eta a by h into v naught. Okay, so from here also you can get the expression for v naught, because without solving the differential equation really. So you must realize, since as when the pulling force will be pulling it down, so it will increase the velocity of the block. As the velocity of the block will be increasing, so you can say that the viscous magnitude of viscous force will also increase. So at a time, it will happen that the pulling force and the magnitude of the viscous force will equal each other. So at that time, the block will be experiencing net zero force. So that will be moving with constant velocity, and that velocity is known as terminal velocity. Okay. So that is one of the problem. One another problem I want to give you is something like this. Let's say again we have a table, okay, and we have a thin layer of liquid above it, okay, whose height is h, okay, and on that thin layer, okay, a plate, a thin plate, okay, which is of negligible mass, you can say, or you can say that is inertia less. Okay, and what we wish to do here is we want to uh, pull this metal sheet with some force F, some constant force F. Okay, and now we are interested in that how much time will it take, okay, for the half of this plate, let's say the length of this plate is L, so for half of the plate, okay, to come out of this edge over here. Means this is the initial situation, the final situation that we are looking at. So this is the thin layer of liquid, and the final situation that we are looking at is something like this. Okay, so half of the liquid will be, half of the this metal sheet will be ahead. Okay, so how much time will it take? Okay, so now you must realize at t is equal to t, if we draw this diagram over here, okay, and at that instant you must realize like this block will be experiencing, let's say this is a square plate over here, so that is L into L. So this block or this metal sheet will be experiencing a drag force due to this liquid over here, whose magnitude F would be given as, or F viscous you can say. So F viscous would be simply given as eta times area. So now this part of the area would be, let's say at any instant this is x. Okay, so this will be becoming L minus x. So that area is going to be x times L minus x, so eta A, and the velocity gradient, let's say this is h and this is at this instant moving with velocity v. So the velocity gradient is going to be equal to v by h. Okay, so this is the drag force over here. So when we are going to write the equation of force, okay, so that is going to be F minus Fv, that will be equal to m times dv by dt. Okay, and the value of F is constant, and Fv we have already calculated. So that is nothing but eta x into L minus x by h, and this v is nothing but basically dx by dt over here. On the right hand side, when you closely look, since I have already given that this metal plate here is of negligible mass, so right hand side would be approximately equal to 0. So here, as you can see, that we have got a differential equation in x and t. Okay, and let's rearrange that. So what we will be getting is uh, sorry, this would be L over here, L into L minus X. So what we will be getting over here is something like um, F is equal to eta L by H into L minus X dx by dt, and let's rearrange that. So that would be, you can say F H by eta L is into dt also you can write is equal to L minus x into dx. So we have separated the variables and now we can integrate both sides. This term is constant, so let's integrate from 0 to t and let's say 0 to x. Okay. So here what we will be getting is t is equal to eta L divided by fh into Lx minus x square by 2 over here. So we have got time as function of x. So in this function, if you substitute the value of x is equal to L by 2, you will be getting your required answer. So this is one of the problems. Another problem here I want to discuss for the linear velocity profile is this. Let's say we have a thin layer of the liquid, okay, whose height is h, and the viscosity of this liquid is say eta, okay, and this thin layer of liquid, we have put a circular plate. Imagine a circular plate that has been kept over it. And let's say at any instant when this is moving with angular velocity omega, so obviously there is a relative motion between this, at any point of contact there is a relative motion between this disk and this layer of liquid over here. Okay, so we wish to find out first of all, let's enlist the quantities we want to find out. The first of all we want to find out the velocity gradient. Okay, and the second thing we want to find out the net torque experienced or net torque exerted by liquid on disk. And the second thing is external torque required to rotate the disk with constant angular velocity. And so first of all, let's try to find out these quantities over here. So now you see, like for example, let's imagine a thin area of radius r and width dr, circular area of width dr. Let me draw that area again. Okay, let's say that is the top view, and this is dr. Okay, obviously, if this is rotating with angular velocity omega, this point will be moving with r omega. Okay, so this point here is moving with r omega. Okay, and this layer of the liquid is stationary. So the velocity gradient, first of all, velocity gradient as function of r, we can write dv by dy. Okay, so dv will be simply equal to r omega and dy here is nothing but h. We are assuming again the linear velocity profile because this h is very, very small. So dv by dy is equal to r omega by h we have got. So due to this, okay, so due to this velocity gradient, and since this is in contact with the liquid, so this will be experiencing, this disk will be experiencing a tangential force. This disk will be experiencing a tangential force, and this tangential force will be, due to this tangential force, there will be a torque acting on this disk over this layer about this axis in this direction. This would be the direction of the torque exerted by the liquid on this disk. And we want to find out the expression for this torque. So first of all, let's try to find out this small torque d tau that will be on this elemental area. Okay, so this d tau is going to be equal to, first of all, the magnitude of force into its r is nothing but r. So the magnitude of tangential force is going to be simply eta times a, area of this thin element is going to be 2 pi r dr, and dy, velocity gradient dv by dy is nothing but r omega by h. So what we have got, let me simplify it, that is 2 pi eta omega by h, okay, into r cube dr we are getting. So that is d tau. So in order to get the net torque, what we need to do, we need to integrate this term, okay, from 0 to capital R, and what we will be getting over here is nothing but pi eta r4 divided by 2h times omega, you can say. Okay, so this tau is directly proportional to omega, you realize. Okay, like for example, tau is directly proportional to omega, or you can say tau is equal to some k omega, whereas the value of k is nothing but this quantity inside the bracket over here. So this disk will be experiencing this much torque due to the liquid. So in order to rotate this disk with constant angular velocity, the net torque acting on the disk must be equal to 0. So we must apply the external torque of same magnitude but only opposite in direction. So tau external is also going to be same quantity. That is nothing but pi eta r square upon 2h into omega over. So this is the idea. And now, since we have found out all these quantities, like what torque it is going to experience, let's look at two simple model of problems. The first special case I am looking at, like for example, if disk is given some initial angular velocity omega naught and no external torque is applied. So in that case, what would be the angular velocity of the disk as function of time? Obviously, since its initial angular velocity is omega, okay, and it is experiencing a retarding torque due to the liquid in contact, obviously the velocity of it will be decreasing with respect to time. So we want to find out the angular velocity as function of time over here. Okay, so in order to do that, we just need to write the equation of torque. So we are going to use this expression, that is tau net external is equal to I, which is moment of inertia, into alpha. Let's say moment of inertia, this disk given here is alpha. So tau net external, you must realize, you can write it as simply minus k times omega, where the value of k is nothing but this quantity in the bracket over here. And why we have used this negative sign? Because it is opposite, this force is acting in the direction opposite to the instantaneous angular velocity, means it is a retarding torque, and that would be equal to I times alpha, and alpha could be written as d omega by dt over here. Rearranging this equation, you can see we'll be getting d omega by omega is equal to uh, that would be minus k times dt by I, and you can integrate both sides with appropriate limits. At t is equal to 0, it is given to us as the initial velocity is omega naught, and at t is equal to t, we want to find out this omega. So solving this differential equation, that will yield omega is equal to omega naught into e to the power minus kt. So you can say that this angular velocity here is exponentially decreasing. So now let's look at the another case 2 here. Okay. So for example, if disk is at uh, rotated by a constant external torque tau naught, and initially at t is equal to 0, let's say omega is equal to 0. So we have started applying an external torque tau naught on the disk, and the motion is being started from the rest. The initial angular velocity is 0. Now again we wish to find out the angular velocity as function of time. So again, we need to write the same differential equation. Tau external is equal to nothing but di, sorry, um, I alpha you can say. So tau external here is going to be equal to this external torque here we are applying, and apart from that, uh, um, the retarding torque will also be acting, so that we have already found out, and that's magnitude is nothing but k times omega. So tau naught minus k omega would be equal to I times alpha would be again d omega by dt. So d omega divided by tau naught minus k omega is equal to k dt divided by I over here. This is the differential equation we have got. And again, we can integrate both sides with appropriate limits. So at t is equal to 0, you can say the initial angular velocity is 0. And at t is equal to t, we wish to find out the angular velocity omega over here. So this will give us simply omega is equal to tau naught by k into 1 minus e to the power minus kt by I. So again, you are very aware of this expression over here. So like after a very long time, the disk will continue to rotate with this much angular velocity. This you can say omega naught, that would be equal to tau naught by k. That would be the terminal angular velocity. Okay, at this instant, the net torque acting on the disk will be equal to 0. So these were few cases we discussed for linear velocity profile. Linear velocity profile, and as I discussed, like the conditions under which that can be applied. So now let's move on the discussion of some non-linear velocity profile also. Let's have non-linear velocity profile. And please realize all of these are basically a good approximation of the flow of the liquid, okay, inside a pipe or wherever. So this non-linear velocity profile we are going to discuss. So for example, um, say there is a thin capillary of say a radius r and length L. Okay, and the fluid is flowing inside. We have already discussed the flow of fluid in the previous chapter, that was fluid mechanics. But over there, our assumption was the liquid is non-viscous. But here, we are going to consider the viscosity also. So, as the fluid is flowing, there would be decrease in pressure in the direction of flow. So, if the fluid is flowing rightward, and the pressure at this cross section is P1 and the pressure at this cross section is P2, and if you apply Bernoulli's principle, P1 is going to be equal to P2. Okay, but that would not be the case over here because this liquid is viscous. Okay, so here what we have is P1 is greater than P2, and let's say delta P. Okay, we are defining it as something like P1 minus P2. Okay, and liquid is flowing. Let's say the viscosity of this liquid is eta. Okay, and we wish to find out certain things. Like first thing we want to find out, let's say this is the axis of this capillary, and let's say at a distance r from the axis we want to find out the velocity profile as function of r. That is the first thing we want to find out. And secondly, we also want to find out the volumetric flow rate of the liquid through the capillary. So these two things we are interested in. So for that, let's imagine a thin layer of liquid which would be cylindrical in this case, you must realize. Thin layer of liquid. Okay, and this cylinder we are having has radius r and its thickness is say dr. Now look very closely. First of all, so here the velocity profile would be, for example, see, at r is equal to capital R, at like the periphery of this capillary over here, the velocity is going to be 0. Okay, so the as we move away from the surface, velocity is going to increase. So the maximum velocity we are going to get is along the axis. Okay, and the velocity here at the extremes are going to be equal to 0. So that you must realize that dV by dr, first of all, you must realize, is nothing but a negative quantity. dV by dr is nothing but negative quantity, and this expression, when we write F is equal to minus eta A times dV by dy, or here in this case we will be writing dV by dr, you must realize that the direction of F is opposite of dV by dr. That is what this minus sign indicates. So now you must realize that here the velocity is, let's say, v, and here the velocity is v plus dv. So this layer's velocity is v and this layer's velocity is v plus dv, and obviously the velocity is decreasing as r is increasing, so dv by dr is negative. So the direction of dv is in backward direction, so that is why the viscous force exerted by the bottom of the, like the inner part of the liquid, will be in this direction, so that is F, and like the upper layer of the liquid will be dragging it in backward direction, so that is something like F plus dF over here. So this layer of the liquid, this cylindrical layer of the liquid, is experiencing this force F due to the inner part of the liquid, and this force F plus dF due to the outer part of the liquid. And also I previously said that the net force acting on the any layer of the liquid got to be equal to 0. So now you must realize, like at this surface, from this side, P1 times dA will be acting, and on in this surface, P2 times dA force is gonna act. So when you consider the overall force balance on this layer of liquid, you will be getting dF in this direction, and then you will be getting delta P into dA into this direction. Okay, and as I said that all the layer of the liquids will be moving with uniform velocity with respect to time. So net force got to be equal to 0. So that you must realize that dF is equal to delta P times dA over here. Okay, and when you will be integrating this both side, what you will be getting is simply F is equal to delta P and integral of dA, and integral of dA would be nothing but pi r square. So delta P into pi r square. So this force we have got. This force we have got. So once we have got this force, now we can find out the velocity profile, because according to the law of viscosity, we know about this force. So when we are going to substitute this expression for force over here, so that is going to be minus eta times A into the velocity gradient into delta P times pi r square. So now you realize what would be A over here. So what is the area of the surface over which it is acting. So the area is going to be the surface area of the cylinder, you must realize. So that is going to be 2 pi r into L over here. So that is eta A, and dV by dy we have yet to find out. So this would be simply dV by dr over here. So this here gives us a differential equation in V and R. So when we will be rearranging that, okay, so what we will be getting over here, that one of the R here will get cancelled and this pi will also get cancelled. So when we will be rearranging, so this dV will be here, and that would be delta P divided by 2 eta L into, you can say that would be R dr, and we will be integrating between appropriate limits over here. So let's say here we must realize that R is equal to capital R, the velocity is 0, and we are interested in velocity as a function of R, so this will be the case, and there will be a negative sign here as well. Okay, so this will yield us that V will be equal to nothing but delta P divided by 4 eta L into capital R square minus small r square. So this is basically parabolic velocity profile. Okay, so let me draw that here also. So if this is the pipe, okay, so the liquid at the axis is going to be moving with the greatest velocity. So this is the kind of profile we are having. Okay, and this is given by this expression. This is known as parabolic velocity profile. And the next thing which we are going to discuss, as we stated earlier, we also wish to find out the volumetric flow rate. The volumetric flow rate through the small cross section dq will be simply dA times V, and dA would be nothing but 2 pi r dr over here, and V we have already found out, and that is nothing but delta P divided by 4 eta L into r square minus r square here. Okay, so if we integrate this equation both sides with appropriate limits, we will be finding out the total volumetric flow rate, and that will be nothing but pi delta P divided by 2 eta L. We can take common, and that would be like r square minus r square into r dr, and limit from 0 to capital R. And solving this, we will be getting this expression, that is pi delta P into r to the power 4 divided by 8 eta L. And this is the expression for the volumetric flow rate inside a capillary over here. And this expression is known as Poiseuille's equation. Poiseuille's equation. Okay, and that is not exactly in the syllabus of JEE Advanced, but as a question they can always ask you. Okay, so this is the idea over here. So this gives the volumetric flow rate of the liquid inside a capillary. And now let's look at this expression closely. Okay, this Q we have already written. It is pi delta P r to the power 4 by 8 eta L. Okay, we can rearrange it like this. Q is equal to delta P divided by 8 eta L divided by pi r to the power 4. Okay, and this can be written as delta P by say some quantity, let's say C. And C here, you must realize, C here is nothing but the resistance of flow. Why we are saying like that? So now when we have written Q is equal to delta P by C here, so we must realize this is very similar to the form that I is equal to delta V by R. That is Ohm's law. Okay, that is Ohm's law that we use in current electricity. That electric current is delta V by R, where delta P here is nothing but the potential difference and R is the resistance. So here same transport phenomena is occurring. So here liquid is flowing due to the difference of pressure. So wherever a difference of pressure is there, liquid is going to flow from higher pressure to lower pressure. Okay, and it will experience a resistance. Okay, and due to which the pressure will decrease in the direction of flow, you must realize. And in that case also, that in comparison to Ohm's law, if we have capillary, one case we can have capillary uh, in series. Okay, so C equivalent, you can write that summation of Ci, and secondly, if you have capillary in parallel, okay, then 1 by C equivalent would be summation of 1 by Ci over here. Obviously, the value of C you realize that is nothing but 8 eta L divided by pi r to the power 4. So it not only depends upon the geometry of the pipe, but it also depends upon the property of the liquid which is flowing inside. Okay. So today we have discussed basically a few problems of linear velocity profile, and we have started the discussion of non-linear velocity profile. In next class, we will discuss some more problem of non-linear velocity profile. Okay, and then we will talk about Stokes law as well and Reynolds number, etc. And this is all for today's class. Thank you very much for joining us.